A warm welcome to all of you. My name is Nida, and I will be presenting the paper titled Management Plane for Differential Privacy Preservation through Smart Contracts. When we consider the challenges in blockchain technology, we think about throughput and scalability issues, but data privacy is also a challenge in blockchain. A review of privacy preserving blockchains has indicated that they are vulnerable to breaches of privacy, and quite a few of the privacy preserving blockchain platforms have indicated that there exists a need for a formal mathematical model of privacy, namely differential privacy. When we think about the usage of blockchain in the European Union, then there should be compliance to the GDPR or the European General Data Protection Regulation, which entails that the blockchain platform should ensure data privacy. What exactly is differential privacy? You can consider differential privacy to be a constraint on an algorithm which is being used to analyze a data set while preserving privacy. So basically, any algorithm that is differentially private would ensure that the analyst remains as unaware about the data set as he was prior to the analysis. So this is basically used when you are thinking in terms of statistical analyzing statistical databases, and here it should be ensured that there is no leakage of data at the individual level in the database. So for example, you send a query to the data set to know what is the mean or the average of all the values, and so you will get to know the approximate average value without knowing anything about the individual data that is present in that particular data set. There are two approaches which are generally used in the context of differential privacy, and we implemented both the approaches in our prototype of the privacy management plane, which is the major output of this research initiative. So the first approach is that of global privacy, where the data owners trust the data curator, and the data curator is the entity that is responsible for maintaining the data privacy. When you talk about local privacy, then the data owners do not trust the data curator. And this is basically used, for example, you can consider the usage of local differential privacy by Apple when it gathers the usage statistics from the smartphones. For example, I'm a smartphone owner, and I have the device, and then there will be an algorithm that will be adding random noise, for example, to how many emoticons I use in a day, or which emoticons do I use before sending that data to Apple. Now, there are some basic concepts that need to be known when you talk about differential privacy. First is the privacy budget, which can be indicated by epsilon. This determines how private the data is. A smaller value of epsilon implies that there is more privacy, but at the same time, the data result would be less accurate that would be received by the analyst. Then sensitivity determines how much noise is to be added to the result. And there are a number of mechanisms which are used to add this noise to the data. And we have considered the Laplace mechanism, which is used to add noise in numerical outputs. This is because we used a data set from a bank, and the data in that, the columns of data that we considered for our implementation, for testing our implementation, were all numerical. Now here you see the design overview of the privacy management plane. The diagram gives the functional architecture. When you look at user A, he is the one who will be demonstrating the global privacy that I mentioned, and user B will be demonstrating the local differential privacy that I mentioned, which is also used by Apple. So when you talk about user A, he sends a query. For example, he wants to find, let's say we use the data set with columns like loan, then payments like the loan amount, then the payments you made towards that loan amount. So he, for example, wants to know the average loan that was given by the bank. So this query passes through the decentralized app that we had developed, and then it goes through a web application which interacts with the data curator responsible for the database. The data curator returns the result of this query through the web application to the decentralized app that we had developed. Now, this web application, before returning the result to the decentralized app, adds Laplace noise to it, and then through the decentralized app, the smart contract inside the decentralized app, the query result is stored on the blockchain platform from where the user A can read this result. Coming to user B, so he is the one who's responsible for maintaining the privacy of his own data. So he needs to add the noise himself. So basically what our decentralized application does here is that it allows user B to send its data to the web application through the smart contract. And now when this data is received by the web application, it adds Laplace noise to the data and then returns the differentially private data through the decentralized app and stores it using a smart contract in the blockchain platform. Now, a demo of this entire privacy management plane implementing the simple query of user A and also a complex query, as well as conversion of the raw data into differential private data has been demonstrated, and the demo can be seen on this link. Now, a very important point that needs to be discussed with regards to our privacy management plane is its compliance to GDPR. There are basically two very important factors when you think about a blockchain in the context of GDPR. The first is that the GDPR requires that there should be a legal entity that is responsible for each data point, so the rights of the data subjects can be enforced according to the GDPR. When we talk about the global privacy, we have the data curator that is responsible for the database. When we talk about the local privacy, then this cannot be implemented using a public blockchain platform. When our privacy management plane is used in a permission blockchain platform, then it would have a legal entity which would be the stakeholders of the permission blockchain platform. Then GDPR is also based on the assumption that the data can be erased or modified when necessary. When you talk about global privacy, the data record exists of the blockchain platform in the database. So, of course, it can be erased or modified. When you talk about local privacy, then you have the differentially private data stored on the blockchain platform. And when you use the privacy management plane in a permission blockchain platform, then you can have an access layer using smart contracts, which can prevent a certain data record from being read by a user. Now, I would like to conclude that the privacy management plane that we have developed, it permits data curators, as in global privacy, to store the query results in the blockchain platform, which also facilitates reuse. Then our privacy management plane also allows individual data owners to choose their privacy budget and store differentially private data on the blockchain platform. Then we also extended the privacy management plane by using another smart contract in such a way that it prevented the data record of a certain ID from being accessed from the blockchain platform. And this is very useful for GDPR compliance in a permission blockchain platform. Our implementation is a basic step towards achieving data privacy and GDPR compliance while providing access to data. And the future work would involve accessing the relational database in a more secure manner. Thank you for your patience and your time.